Okay, so in the last few lectures, we've been talking a lot about electric fields and various ways to calculate electric fields. So, for instance, using Gauss's law to calculate more complex charge distributions, or the fields from complex charge distributions like, planes, spheres, cylinders, things like that. So, if you remember kind of back to learning mechanics, if you wanted to, understand the dynamics of objects, you could basically get away with just using forces all the time. You might have to do integrals to basically calculate the behavior of these objects all the time, but you could do it with forces, but it's just not necessarily the most elegant way. And so if you remember something like when you were learning about probably gravitational forces, you learned about things like gravitational potential, potential energy, and things like that. And it turns out that in the case of electrostatic forces, it's also very useful to think about things like electric potential and voltage. And so that's what we're going to spend the next couple lectures learning about. And so, in that sense, it'll help us to understand the behavior of, charged particles and electric fields without having to do, very complicated integrals for all the equations of motions of charged particles and electric fields. We can basically just, get them just by looking at how the energy in a system may go from potential energy to kinetic energy or vice versa. So the fact that we can define electric potential is because the electrostatic force, as described by Coulomb's law written up here, is a conservative force. And a conservative force is defined as one in which the work done in moving an object from point A to point B does not depend on the path taken. It only depends on the endpoints A and B. So for instance, you could go in a straight line from A to B. You could take a big, circuitous route or a curved path from A to B, and it wouldn't matter. The work done would be exactly the same. So some conservative forces that you have learned about already are the electrostatic forces that you learned about in this class, and gravitational and spring forces that you learned about in your mechanics class. Some non-conservative forces are things like friction or drag forces, and you can think of why friction is a non-conservative force. If I have a big heavy box and I pushed it in a circle, let's say I pushed it in a big circle, but the box ended up exactly where it started. The start point and the end point are the same, right? But I did some work, right? But you could imagine a second situation where I don't even touch the box, but the starting point of the box and the ending point of the box is the same because the box never moved, right? In that latter situation, I didn't have to do, there was no work done on the box. In the former situation, there was work done because, you're tired and sweaty because you were pushing this box for 2 hours. So clearly, friction and things where, the amount of work done is path dependent are non-conservative forces. One very brief aside, and this is not going to be covered in the course, but it's sort of an interesting side note, is that all the microscopic forces that exist in the universe, like the electrostatic force, the strong and the weak, nuclear forces, the gravitational force, these are all actually conservative forces. So every force that actually exists is in actuality conservative. So then where do these so-called, quote, non-conservative forces like friction come from? So that's a little bit subtle. Friction actually is an electromagnetic force. It's basically the interaction between a molecule on the bottom of the box and a molecule on the floor, and they're rubbing together, and they're basically causing the atoms and the electrons inside the boxes to vibrate. And that increases, for instance, the kinetic energy of the molecules, the vibrational energy, and maybe the temperature of the box, because basically the vibration of molecules is heat. So if you actually accounted for all these sort of hidden internal degrees of freedom in the box that we don't normally think about, you can actually show that in fact energy is conserved. But usually when we think about a box, we don't think about all the little particles inside. We don't think about the temperature of the box. So in effect, we think of friction as being non-conservative, But at the end of the day, if you really wanted to go into detail and look at basically where the energy is being distributed, you would find in reality it's all conserved. Again, that's sort of outside the scope of the class, but it's sort of an interesting aside. Okay, so what I want to do now is to talk a little bit about work and potential. So this is something that you will likely have already seen in your mechanics class, but I think it just bears a little bit of sort of repetition, at least briefly. So let's imagine we have some field. All right. So let me just write something down here. So we're going to talk about work and potential. And so let's imagine some field that we can define from some conservative force. So let's just say hypothetically this is some kind of gravitational field. Okay, so it's the gravitational field near the surface of the Earth, which you can basically, to a large extent, approximate as constant. At least when you're close to the surface of the Earth, right? So I'm going to draw something like a hill. Like this. And so let's imagine you have, a rock. And so, you have a rock here. You pick it up and you roll it up onto the top of the hill. We're not going to worry about friction here, so this is 1, right? And let's say this hill is some height h. And then sitting here, and then eventually you nudge, and it rolls down the hill. Right now it has some kinetic energy, some velocity going this way. Okay, so this is step 2. And in fact, what I'd like to do is to, let me just actually rename these. So I will call this actually step 1. So I'll call this point 1 here, where it's sitting, point 2, where it's perched on top of the hill, and point 3 here. Okay. So let's consider, step 1, and then in going from 1 to 2, so in step 1, if we remember, we're just going to say that this thing starts at rest, okay? So it basically starts at rest. In going from 1 to 2, we do some work on the system. So we have to do some positive amount of work to push this thing up the hill, right? So basically, if you remember, so let me just write it like this. So basically, the work in going, and we will write it like this, from 1 to 2, backwards, done by us. So I'll write us up here, just so it's clear that what's going on. So we're doing some positive work to push this rock up the hill, right? And you may recall that basically this is written as basically the integral of some force exerted by us dot dl going from 1 to 2. Okay, so write a vector here. So at position 2, basically the object is at rest again. But now it's acquired some, in this case, some potential energy, delta U. All right, and that gain in potential energy came from basically the work that we did in pushing this thing up the hill. So, for gravitational energy, this would be like mgh, right, where this thing has some mass m. And it would be a positive mgh because the object is at a higher position, right? And then now when we let it go from 2 to 3, so let's say it just barely makes it up we just get it up the top of the hill. It has almost no kinetic energy, just a teeny little bit, but then it just starts to roll off the edge again. So now there'll be some work done, by the field, by gravity, going from 2 to 3. Which I'll write like this, 2 to 3. And this is the force of gravity dot dl. So at the bottom of the hill, in situation 3, now basically, it now has some kinetic energy. But now it has lost potential energy. And in fact, what happened is that the potential energy gained, delta U, in rolling it up the hill, went into the kinetic energy it has now at the bottom of the hill. Right? So for instance, we can define something like, so let's consider positions 2 and positions 3. So the energy, total energy E2 at position 2 is basically the sum of the kinetic energy plus the sum of the potential energy. This was 0. And it's equal to, because this is a conservative force, the energy at E3, which is equal to K3 plus U3. I'll just define it such that the potential energy when you're sort of at ground level here is 0. So I'll write that as 0. Right? So basically you can see how potential energy at the top of the hill goes into kinetic energy, right? And this is, of course, I think, something that hopefully you're all familiar with. So here's an important thing to note. So if we think about the kinetic energy now, so basically the kinetic energy of the system is basically, okay, let me just actually change this here. So let's consider now in going from 2 to 3, we lose some potential energy, right? So I'm going to make this a minus delta U. So we've lost some potential energy when we roll down the hill. And that lost potential energy is basically the work equivalent to the work done by the field in going from position 2 to position 3. And that, of course, that work done by the gravitational field is, of course, going into the increase in kinetic energy, right? So in other words, we have an expression here which is basically the change in potential energy U is minus, and this is the, let me just rewrite this here. Delta U, some room for subscripts, in going from 2 to 3. And this is for some generalized force. So this is not now, the force of U. It's the force from a field, dl. And I'm just going to write 2 to 3 here. All right. Or in other words, just for any two generalized positions, it's delta U, we'll say going from A to B, is going to be minus the integral from A to B F dot dl, okay? So this is true regardless of whether or not we're dealing with a gravitational force, an electrical force. The example I started with up there was a gravitational example just because, that would probably be most familiar to you. But let's imagine now that instead, in this example here, instead of being the red dot being a stone of mass m, it was, let's say, a charge q, and sort of the exact same thing applies. If I moved q up, so the electric field is pointing down this way, so which means that q would want to basically accelerate in the direction of the electric field because we're defining q to be positive. If now I could do some work and basically push the charge upstream to position 2, and then I could let it go, right? And let's say there wasn't this hill here, so I could just move it up to position 2. I could let it go. It would basically now accelerate down. The potential, it would gain some potential energy in being moved upstream against the field. And when I let it go, it will basically now flow downstream with the field. And that potential energy, delta U, would be converted now to the kinetic energy of that particle now being accelerated in the field, right? So basically, if I replaced basically F, so the first example we had was sort of F is equal to mg, but we have an exact analog for electrostatics, which is F would be QE, right? And everything, it works exactly the same. G goes to E and M goes to Q. So in that case now, for electrostatics, we would have the situation that delta U, the change in potential, and I'll write that as BA, is going to be equal to minus A to B Q times E dot dl. All right. And I'm going to factor the Q out. So this is a lot like what we did for the when we defined the electric field, right? We had the definition of Coulomb's law, so we had a force, and we factored out a Q to get an electric field. And now I'm going to factor the Q out of here. So basically I'll have something that looks like this, minus A to B E dot dl. Okay. So we call this basically a voltage V. Going from B to A. All right. So again, the reason why we've defined this potential is that basically if I basically take some charge Q and I move it in some potential, and I want to basically know what the change in potential energy of that charge is, I basically, all I need to know is the potential. I can basically, for whatever, I can substitute, for whatever charge, so let's say I start off with a charge that's the charge of 1 electron, then I change that to a charge that's maybe, 1,000 electron charges. I don't have to I don't have to recalculate this, right? As long as I know the voltage, all I need to do is plug in the value of the charge, and that's basically the change in the total electric potential energy. Okay? So again, it's very much like what we talked about for electric fields. If I wanted to get the force, all I need to know is the field for a given charge, and then I just multiplied by the magnitude of that charge, right? And if I change that charge, I don't need to redo the calculation. I just multiply it by the electric field. So it works exactly the same for potentials, right? There is one very important difference between the analogy between masses in a gravitational field and charges, and that is that because masses are always positive, we don't have negative masses. If I have a mass in a gravitational field, it will always accelerate in the direction of the field. So basically, if I look at this example here, higher potential is always going to be against the field, right? So higher potential is always going to be, let's say, up higher here, and lower potential for a mass would be down here. That's also true for a positive charge, right? So if the green lines, instead of being a gravitational field, were an electric field, then basically a higher potential would be up here for a positive charge, and it would be down here for a negative charge. But then if I think about a negative, it would be up here, higher potential would be up here for a positive charge, and lower potential would be down here for a positive charge. I'm sorry, I misspoke there, okay? But then if we consider the case of, now we can have also negative charges. So I'll make this minus Q. So basically, if I consider what the force of a negative charge is in an electric field, right? Basically, F is basically Q times E, but then if I have a negative Q, then the force is going to be opposite the direction of an electric field, right? Because the electric field is always kind of defined as the force that a positive, it's always going to be in the direction that a positive test charge will feel the force. So if I have a negative charge, the force that the negative charge experiences will be opposite the direction of the field, right? So if you imagine I put a negative charge in this field here, it will want to move upwards and not downwards like the positive charge. So what that means is that basically for a negative charge in this electric field, basically that the higher potential is now at the bottom, and the lower potential for the negative charge is at the top, right? Because if you think about this analogy with the mass, objects always want to go from a higher potential energy to a lower potential energy. So for a charge, a positive charge, Q here, that means it will want to move from a higher potential here to a lower potential here, just like I've drawn here for the mass. But for the negative charge, it would want to move in the opposite direction. Okay, so for the negative charge, the higher potential is down here, and the lower potential is down there. And so if I put this charge in the field, it would want to move this way from higher potential energy to lower potential energy. Okay? So basically, objects always move to lower their potential energy. Okay, so now I'm going to take the example of a point charge. Actually, I'm going to start a new page. So let's imagine we have a point charge, positive Q. So there are some electric field lines. Like this. And we want to basically calculate what the potential is for this point charge, okay? So the idea is I've got this point charge here of charge plus Q. So the electric field lines are going out. And basically, let's say I have another charge. So let's say, so I'm going to draw this kind of wavy break as saying this is going out to very far distances. So I have a point charge, a test charge here. So this is plus capital Q. I'll call this plus little q. So whenever we're doing these, calculating these potentials, then we always use positive test charges. Okay, so the idea is then, how much work would it take for me to now move this positive test charge from infinity, let's say, to some point, a distance r, so this is some point p, to move some distance r away from the point charge. Okay? So basically I'm going to take this guy and I'm going to move it all the way to point P, and how much work does that take? So basically what we have here is that, so delta U going from, we'll say, infinity to R, right? That's going to be equal to the magnitude of charge on this test charge, little q, times V, and I'll write V as going from infinity to R. And we define V as basically being minus the integral from infinity to some position R of E dot dl. Okay? And so we'll say this thing is moving just along the x-axis. So this is the, x-axis. And like I said, for conservative forces, so, we have basically one. So I'm going to calculate it for sort of the simplest path, which is basically going. Oh, that's a bad line. So that wasn't much better. Going like this. But I could also imagine another path, let's say that was going like that. Or another one that was going like that. They would all be the same. Right? That's the definition of a conservative force. And I'll show that in a little more explicit detail later. Okay, so since we're basically, like I said, just going along this along the x-axis, this basically reduces to a one-dimensional integral. And like I said, you could take it along any arbitrary path, but we're just going to take the simplest one for now. So it's going to be q minus infinity to position r, little k, which is Coulomb's constant, big Q over x squared dx. All right. And we're integrating sort of backwards from, somewhere way out here at infinity all the way to a distance r away. So what that's going to be is basically, and again this is V r to infinity. So when I integrate this, I basically get a minus kq over x, but there's another minus here, right? So a minus minus gives me a plus, so it's going to be kq over x. Evaluated at infinity and r. So delta u r infinity is basically equal to, so little q times this, right? So basically it's going to give me, and this is written as v going from infinity to r. So it's going to be q times just k big Q over r, right? Because I have kq over r minus kq over infinity. That's basically just 0. All right. So basically this here is the change in potential energy, this whole thing, bringing a charge from infinity to a distance r away. From our point charge, from Q. So this thing, this quantity here, I'll just write as V of R, okay? And I'll explain that in a second. So basically, what I can do is I can assign a value of the potential everywhere in space. And, here I said, okay, V is going from some position to another position. And that's the way a potential is always defined. But for a point charge, typically what we would do, so we need to, it's handy to have a reference point. So for a point charge, we say the convention is that V at infinity is 0. The voltage, all right, so basically then, V of R minus, so, this is V of R going from infinity to R. If, V at infinity we said was 5, I would just add, to get the absolute value of the potential, I'd add 5 to everything, right? But basically what we say is that, because very far away, the influence of the electric field is very weak. So we say, okay, very far away, we'll say the potential due to that point charge is going to be 0. So then I can define a V of R, and it's not relative to anything, because basically implicitly it's relative to V at infinity being 0. Okay? So what we have now then is basically the potential V of R for a point charge is just kq over r. And so this was V of r somewhere on the x-axis, but because this problem has perfect spherical symmetry, it could be any position, some distance r away from the point charge, right? I could just redo the entire problem by rotating my coordinate system so that my x-axis always kind of came out wherever, was always aligned with the point of interest. So basically this thing has perfect radial symmetry, okay? Another important thing to notice is that the voltage, V of R, is a scalar. It does not have a direction like the electric field. And you can see that I get the voltage by integrating E dot dl. So that this is a dot product, right? A dot product of two vectors gives me a scalar. So this thing is a scalar. So instead of the electric field being a vector field, right, at every point in space, the electric field has both a magnitude and a direction. The potential basically only has a magnitude. So V of R is a scalar. So actually that makes it a lot easier to deal with than a vector field. So it's, you just add up two scalars. So if you had two point charges, you would just add up V of one and V of the other, and you would not need to worry about the vector components like you would for the fields. So what I'm going to do now is to actually just draw what the V of R looks like. And again, just the voltage is basically, so now what it is it's defined basically as the amount of energy it would take per unit charge to bring that charge in from infinity to some point R, right? And so you can think of it this way, right? That this charge, this positive test charge, the field is wanting to push it away, right? So if you want to bring it in close to the point charge, you basically have to push against the field, right? You have to kind of swim upstream, if you will. And I'm going to make a little graph here just to illustrate that. So I'm going to plot. Oh, that was terrible. Wasn't much better. Yeah, that's a little better. So crap. All right. V of R. So this is for a point charge. Versus R, where this is R is the radial distance away, okay? And I'm not going to worry about it going to minus R. I'll just, so R is equal to 0 is exactly where the point charge is, right? And so KQ over R will look something kind of like this, right? It'll diverge near R equals 0, and it'll look something asymptotically go to 0, but never quite reach it, right? So this is what V sub R looks like. So, let's imagine that I'm somewhere way, way out, so I start with my positive charge Q way out here. So this is basically, more or less at infinity. And, if I want to bring it in to closer to that positive plus Q point charge, so let's say I want to bring it into some radius, big R away. You can think of it basically like kind of having to roll it uphill, right? So this is what V of R looks like. And so basically the electric potential energy that it has at this point is basically Q times V of big R, which, so it's basically just K big Q little q over capital R. But basically, you have to roll it uphill in order to bring it close, right? Because at every point, the electric field is trying to push it out to higher R because the electric field is pointing outwards, right? So if we had a negative charge, and I won't go through the whole derivation in gory detail, but let's say we have a negative charge here, right? So now the electric field is pointing in. We always define the when we always kind of do these thoughts for basically the potential, we always take a positive test charge plus Q, right? So now you can see this positive test charge will want to be attracted to this negative one, right? So then if basically, I do everything here, it's all the same, except my electric field is pointing in the opposite direction. So in the end, I do the exact same calculation, and what I get is that V of R for a negative charge minus Q is going to be just minus K big Q over R, right? So again, if I'm going to make the graph for the negative point charge, and actually what I'll want to do is I'll want to continue it down here. It's going to look like this guy, this plot here, but just flipped. So like that, right? So it'll be diverging as we get close to Q equals 0. And so you can think of it this way, right? If I have a positive charge plus Q, it will be attracted to the negative charge. So it will basically want to roll downhill towards the negative charge, right? It will want to follow the field line. So let's say when it's reached some distance r away, right, then basically it will have lost some kinetic energy, or it will basically have lost some potential. So basically the change in potential now is still Q of this little test charge times V sub R, but V sub R is now negative, right? So it's minus K big Q little q over R, right? And so that loss in potential energy basically has been converted to kinetic energy. So the kinetic energy of the particle then increases by K big Q little q over R. Okay, so now I want to just talk very briefly about the relationship between the electric field and the voltage, how to get the voltage, or how to get the electric field from the voltage, and also how to get the voltage for, arrangements of charges. Okay, so now I want to talk about how the principle of superposition also applies for calculating voltages as well. So let's imagine we have a number of charges, and we want to calculate the voltage, the electric potential, at a particular point due to all these charges. So superposition of voltages. So let's imagine we have a number of charges. So let's say Q1, Q2, and Q3. It could be positive or negative, it doesn't really matter. And let's say we want to calculate the voltage at a particular location in space, we'll call P. And so the question then is, how do we do this, right? So, okay, so, the first thing we can do is to calculate the total electric field. So this would be the electric field from E1 let's say this might be E2. This might be E3. That was from E1. So in that case, the total electric field, so if I was going to do, let's say, a vector addition of these, I would add E1 plus E2 plus E3. So I might have a vector that looks something like this. Right, this might be E total. And from before, we know E total is just the vector sum of all the individual vector component, all the individual vectors, right? So E total, in this case, it would be E1 plus E2 plus E3. In general, it would just be a sum over however many individual charges you have in your system. So if you had n charges in your system, you'd sum over I charges. You calculate just E sub I, right? So we learned this a little while back. All right, so let's say we wanted to calculate now what is the voltage at this position V sub R. Let's say the origin is at some point, it doesn't really matter where. So V sub R, right, was defined as minus the integral, and we're always, when I write V sub R, it's implicitly saying it's going to be coming from infinity to point R, where the potential at infinity is defined to be 0. That's kind of our reference point. Of E total dot dl. So what I can do then is I'm just going to write out what E total is in terms of all these vectors. So let's say, just take this example where you've got those 3 vectors there, got the minus sign. So it's E1 plus E2 plus E3. Dot dl. All right. So we know that if we have an integral or a dot product, we can still write it like this. We can still write it like minus E1 dot dl, again from infinity to R, minus E2 dot dl minus E3 dot dl, V sub R. Right, so we've now broken these up so that actually, E1 doesn't know about the other charges. So this is really just V from charge 1, R1, where R1 would be the distance from Q1 to point P, plus V2 R2 plus V3 R3. So in general, if we have, n charges in our system, I'll call it V total, which was just our V sub R, is just going to be the sum of the individual voltages for each point charge in the system, V sub I, R sub I. So if I'm doing the finite sum, then this just looks like, if I replace V sub I by, the expression for the potential form of point charges is KQ sub I over R sub I, which, if we were going to make this an integral, so this again is over the charge distribution. You're basically integrating K dq over R. Okay? So, in a nutshell, superposition also works for voltages. It's actually even easier to employ than for electric fields, because actually the voltage is a scalar. So this R sub I is a distance, this V is a scalar, so you're just adding up magnitudes. You don't even have to worry about breaking up into directional components like you would in for electric fields. Okay, so basically the principle of superposition works for voltages, and the other thing is that you just need to add up the magnitudes. So the things that we care about are just the distance from here to here, not the vector, but just the magnitude of this vector. And you just basically do a sum over all the charges in the system, or an integral over the charge distribution. So it's similar to what you would do for electric fields, but in fact even easier. So the last thing I want to talk about on this video is just a quick kind of proof or demonstration as to why, let's say, the electric field from a point charge, and in fact all electric fields, are conservative. So I kind of gave a very hand-wavy argument for that at the beginning of this video, and now I'm going to give a slightly more in-depth discussion of that. And I will not talk about how you get electric fields from voltages in this video. I'll put that off to the next one, because this video is getting a little on in length. So let's imagine we have a point charge. And if you've already seen this for gravitational potentials and you remember this, then you don't need to watch this part of the video if you recall the sort of argument for gravitational fields. Right, so this is just arguing why electric fields are conservative. So let's imagine we have a point charge plus Q. And, let's imagine we're going to go from some point here, which we'll call A, to some point here, which we call B. And if it's conservative, it means that the work, let's say the work done by the electric field in moving a test charge from A to B, let's say along this line. Oops. Okay, so this path here, so I'll call this path 1, would be the same as, let's say, a path like that. Okay, just some arbitrary curved path. So if we wanted to first calculate the work, so for path 1, the work done by the field in going from A to B is going to be equal to the integral of the force exerted by the field dot dr starting from A and going to B. All right. So this first path is exactly along, just exactly parallel to the field line. So that's relatively easy to calculate, right? So we know then the field strength is just K big Q over R squared, right? And the vector is R hat. But then basically we're going to dot this with, so dr is the scalar and then R hat is the direction, because basically, you know, the electric field and the path are exactly in line with each other. So we get an R hat dot R hat, so that's just 1. So we just basically all we're doing now is just integrating KQ over R squared dr from A to B. All right. So that's very straightforward. So we basically, the integral of this is just minus KQ over R. Evaluated in A and B. So we'll call those positions to be basically, so it'll be KQ over R sub A minus KQ over R sub B. And you know, in order to switch because it was a minus KQ would be minus KQ over R, right? So first, for starters, this is a positive. You know, we're moving with the field. So this, of course, should be a positive quantity. You know, R sub A is smaller than R sub B. So indeed, this will be bigger than that, so it will be positive. Okay, so that's pretty straightforward. That's just the straight line. So now let's take this path 2, okay? So again, I'm just going to write, you know, it's the work going from A to B done by the field. We're calculating exactly the same thing. So the first part that we're writing is going to be exactly the same. But the path may not be perfectly radial, right? So let's take a look at one particular point on the path. So let's look kind of out here somewhere, right? So now I'm just going to zoom in on this little segment here. So DL might look like this. Right, so here's DL. But the electric field, let's say, might be coming out at a bit of an angle. With respect to, we'll call it some angle phi. Right, so now the electric field is making some angle with DL. And the electric field, of course, is radial, right? So this would be, you know, a line. This would be a vector. So E is coming, you know, sort of radially out here. So this is dotted with DL. So if we look at this, right, the projection of DL onto E, which is basically what we want, right? Because we basically want E dot DL. Well, that's basically just, it's basically just going to be, oops, E times cosine theta, the magnitude E, times dl, right? Because basically if we're taking the projection of E onto dl, we're just basically taking the cosine of this angle. So, what we're going to write here then, so this quantity I can write here is just going to be something like a to b kq over r squared. That's basically E, and then I get a cosine theta dl, right? Where dl is this curvy path. But basically at every single point, and I think I was writing theta when this was actually phi, so let me just change this vector here, or change this angle to a phi, or to a theta, I'm sorry. So dl cos theta is actually just going to be dr though, right? Because dl is coming out at some sort of random, at some angle, which is not necessarily going to be radially outwards, but E is radially outwards. And when we take dl cos theta, we're basically projecting dl onto the radial vector, okay, onto the radial direction. So basically dl is nothing more than, dl cos theta is nothing more than dr. So what we get is basically then the exact same form as we get over here. So we just get then the integral of a, b. So this is, for every little segment. So theta could be different at every little point on here, but the argument still works. So whatever theta is, cosine theta dl is still basically dr. So we get something that looks like kq r squared dr. So then all these steps are all the same. So basically the work done is still 1 over r sub a minus 1 over r sub b. So to make a long story short, basically the work done in going from B to A is path independent, and therefore the electric fields are conservative. Oops. So again, just to recap, so we did a calculation where we had a path that just came out radially out from the point charge from A to B. Another one where we take some kind of circuitous path. And what we found was that if you consider basically this dot product, which is basically the electric field is always coming out radially, so it may not be parallel to the little segment of the path that we're interested in. This dl, when you take the dot product between dl and r hat, you get a cosine theta term times our path length. And basically when you project, because this angle is basically between the path that we're taking and the radial direction, which is what the electric field is pointing in, this is basically a projection onto dr, which is, defined to be purely in the radial direction. So then basically this integrand ends up looking exactly like the one where we're taking the straight path and everything works out.